There's a mysterious set of chemicals that flow through every part of our bodies. They can rule our lives and shape our destinies. They turn children into adults, they govern our appetites, and they even affect our passions. They are called hormones, and they are fundamental to making us who we are. I'm John Wass, a professor of endocrinology. That's the study of hormones. Hormones have been my professional life for 40 years, and they're absolutely fascinating. To a greater or lesser extent, they control everything in your body. How we unraveled the way hormones work is one of the most fascinating stories in the whole history of medicine. It's a story that involves bizarre experiments and quite remarkable characters. Along the way, there have been some horrific wrong turns and some of the worst examples of opportunism and quackery.
That's his sperm in liquidum. Hormones of 2 testicles.
But there have been some inspired moments of genius and heartwarming tales of survival.
And here's a picture of Leonard Thompson, and he should have been dead.
Today, hormones are at the cutting edge of medical science, and almost daily we're learning that their effects are more widespread than we ever imagined. For me, this is a personal journey as well. It's a story I've wanted to tell all my life. To share and instill my enthusiasm for this subject, which affects each and every one of us, is the most wonderful opportunity. Hormones are a crucial part of our biology, and to understand them is to better understand ourselves. We've all heard of hormones, but most of us don't think about them every day. And for something so fundamental to our lives, our understanding of hormones is remarkably recent. The hormone system isn't an anatomical thing like the skeleton, like the nervous system, like the cardiovascular system. It's something which you don't see, so anatomically it's different. I mean, it's easy being a cardiologist. They have pain in the chest. There's something wrong with our heart. But with endocrine conditions, it's completely different. And I think that's one of the reasons why it's one of the last of the systems, if you like, to be discovered. This endocrine or hormone system, though invisible, is one of the most important factors in running and regulating our bodies. The way we uncovered its secrets is a great medical detective story. It's full of unexpected twists. And I'm going to pick up the trail in the 1730s. Not with a great doctor and a brilliant experiment, as you might expect, but in one of my favorite cities on the planet, with a really surprising story. In all my years as a doctor and an opera lover, I never dreamed I'd be standing on the stage of the Theatre an der Wien, one of the world's great opera houses. I want to play you an extraordinary sound. Believe it or not, this is the voice of a grown man, over 6 foot tall. Made in 1902, this is the only recording of a singer of this kind. But arguably, its greatest proponent lived in the 1730s. He was a true musical star, and his name was Farinelli. This is the sound that Farinelli would have made. almost supernatural, amazingly pure, gentle, sublime, and yet forceful, because he was a fully grown man. The reason for this extraordinary voice is that he was a castrato. Farinelli was castrated before puberty in order to maintain the purity of that voice, which didn't break. When a boy reaches puberty, his voice can drop by as much as a whole octave. Making him unable to hit the high notes of the soprano range. But since Farinelli was castrated before this change could happen, his voice remained high, even as he grew to full adulthood. Amazingly, this shocking procedure continued into the early 20th century. And for many boys, castrated in the hope that they would be the next Farinelli, the effects were both dramatic and permanent. It wasn't just his voice. There were other really important changes, which you can see in this wonderful painting. You can see that he had a straight hairline like a woman and didn't have the V shape of a man. He's covered his lack of an Adam's apple with a silk scarf. And castration even affected how much Farinelli grew. He had an enormous chest. Also, his really long arms. And the legs, too, will have been very long. They carry on growing. And all of this because of castration. Castrati serve as a very dramatic demonstration of what happens when you remove the testicles or testes from humans. And of course, people had observed the effects of castration on cattle for centuries. But amazingly, there was no scientific explanation for why this happened right into the 19th century. So this is the big question that completely baffled people. How on earth could the testes affect so many parts of the body, from your vocal cords to the length of your limbs? Talk about a fall from grace. I've gone from grand opera to chasing chickens. But there's a good reason. In 1849, a German physiologist called Arnold Berthold did some extraordinary experiments on chickens, which would reveal the mechanism by which castration could affect the whole body. Berthold was the professor of medicine in Göttingen, that well-known university town in the middle of Germany. And he also ran the department of zoology, where he came across some birds called capons. The capon's meat was incredibly tender, a real delicacy in early 19th century Europe. And the reason for this is, like a castrato, they'd had their testes removed. Castration had a wide variety of effects on these birds. Compared to regular cockerels, they became docile, meek even, and lost all their sexual appetite. But the main reason Berthold chose capons for his experiments was because they had an obvious physical marker, which made them easy to tell apart from cockerels, even at a glance. This is Bernard, a real bloke of a bird, and I can tell you he's itching to chase hens. You can see his aptly named comb on the top of his head, his wattle under his beak. He's a full-blown male. Capons were completely different. They had droopy combs and droopy wattles. Armed with this simple measure of masculinity, Berthold began a series of experiments to see if he could halt or even reverse the effects of castration.
What he wanted to do was try and reverse the changes that had gone on. So he took the testes out of young cockerels. Then what he did was to transplant testes into cockerels, not within their normal place in the body, but in the abdomen. And surprisingly, he found it would maintain their sexual activity, their aggressive behaviour, and also maintain their wattles and combs.
With these birds, Berthold now had a way to answer the completely crucial question: how were the testicles able to affect distant parts of the body?
When Berthold came to do the autopsy on these birds, he found, quite surprisingly, that the testes that he'd put back into the abdomen had redeveloped their own blood supply. The blood vessels had grown round the testis. So the key deduction was that whatever effects were happening through the blood.
And what Berthold showed, interestingly, were there were obviously some chemicals released from the testes that reacted at other parts of the body.
We now know that Berthold was seeing the action of the male sex hormone testosterone, which, released into the blood in huge amounts at puberty, effectively turns boys into men. No one had any concept that chemicals alone could have such a dramatic effect on the whole body. But strangely, his findings didn't have much impact on the broader scientific community. And Berthold himself didn't conduct any further research into what he'd seen.
These were fabulously interesting observations, and it's interesting that Berthold really didn't seem to think very much as to why they had occurred. So it was a huge missed scientific opportunity. And it was going to be many decades before there was an explanation.
In the 20th century, scientists would rightly acknowledge Berthold as the first to describe how the testicles work. But sadly, his contemporaries ignored his findings. Instead, they made bizarre claims about the testicles, and in particular, for men at least, they thought they might be the source of eternal youth.
Brown-Séquard's method.
This extraordinary advertisement from the early 20th century claims to have found the power to rejuvenate old men.
Populous. Hormones of 2 testicles. This is so funny.
The story of this ridiculous claim and its surprising consequences begins in 1889 in one of the most august institutions in Europe, the Academy of Sciences in Paris. At a very formal occasion, a serious audience came to hear the announcement of one Charles Edward Brown-Séquard.
At the age of 72, and at the end of a long and distinguished career as a scientist and a doctor, he will have been familiar with the wonderful surroundings in the Grande Salle de Sciences, the Academy of Sciences in Paris, as a large number of eminent professors gathered to hear him speak.
What Brown-Séquard announced was a truly unbelievable experiment. He said he had prepared a concoction of the following 3 ingredients:
blood of the testicular veins, semen, and juice extracted from a testicle, crushed immediately after it has been taken from a dog or a guinea pig.
The resulting blood and semen mixture he injected into himself. This is what he told his astonished audience, that he'd more strength and stamina, his concentration powers had improved, and as well, his mental energy was considerably better. Apparently, there was shocked silence in the audience. But with an average age of 71, you can just imagine them thinking, oh my goodness, that would be good. This had the potential to be the elixir of life and a possible breakthrough of the century.
The announcement sent the media into a complete frenzy, And with the public demand for this kind of cure-all remedy soaring across the globe, the papers were filled with articles and advertisements about it alike.
Brown Séquard was headline news throughout the whole world. The press asked, was this a genuine elixir of life?
Of course it wasn't. But it was a call to arms, signalling the start of a period of intense interest in the testicles and other related organs, whose extracts people thought could be used for medical purposes.
By tapping into the public thirst for miracle cures, Brown Séquard created a real phenomenon. This was called organotherapy and involved the injection of various glands into people, often with very little scientific evidence, to cure various illnesses.
But in the case of Brown Séquard, no one was able to repeat his results experimentally, and the dramatic effects he had claimed on his own body must have been down to nothing more than a placebo effect.
Unfortunately, it's unlikely that the watery extracts would have contained any active substance at all.
So, Brown Séquard's extract couldn't possibly have worked. But the great interest it inspired in the effects of gland extracts did have lasting consequences. Throughout the next decade, the 1890s, there was a whole series of genuine scientific breakthroughs, ones that are a vital and extremely gratifying part of my job today.
So this was a woman I was treating who had an underactive thyroid. And one of her children sent me a card, "Thank you for listening to my mum and giving her back." And then her mother wrote, "I cannot thank you enough for giving me my daughter back, my grandchildren their mummy back, and my son-in-law his wife." And all I'd done was to give her thyroid hormone.
Lovely though it is to be thanked like this, I really don't deserve it. The real thanks should go to a pair of pioneering British doctors from the 1890s. They were the first people to actually use hormones to cure up until then what was a debilitating and horrific illness.
This was the story of the first scintillating discovery which resulted in a successful treatment in endocrinology, and it relates to the thyroid gland in the neck.
The treatment focused on disorders known as myxedema and cretinism. They're in fact similar conditions which can leave sufferers physically and mentally disabled. They were relatively common even 100 years ago, and cretinism even featured as a tick box on the Victorian census. Fortunately, it is a disease that is completely manageable today, and that's because of the work started by this man.
Victor Horsley was born here in sunny old London into a family of artistic aristocrats. But he had a huge social conscience and was a forcible advocate of free healthcare for all. But for me, his most important work was on the thyroid.
I'm going to explain what he did with the help of some props. These are sheep's thyroids, although when Horsley began his experiments, he used monkeys.
And what Horsley did was to remove the thyroid from some monkeys and showed that they developed changes of myxedema just like humans. Their hair fell out and they became more lethargic.
With this proof, Horsley conclusively demonstrated that myxedema was caused by thyroid deficiency. But beyond this, he then went on to suggest the bold step of transplanting tissue from sheep's thyroid, just like these, into human patients. Others across Europe took up the call, and the practice of transplanting sheep's thyroids into people had some success. But this still wasn't a cure. It was potentially dangerous surgery, and the benefits were short-term.
So this was the problem. You can't carry on giving this every 7 days, and the effects only lasted for that time. So the question was, how do we make that into a treatment?
It actually took the work of one of Horsley's students, George Murray, to solve this problem in a highly unusual way.
Murray's solution was to cut the thyroid up into tiny little bits, put them in carbolic acid, stopper them overnight, and then use a common or garden handkerchief. And he used this handkerchief to strain these bits and produce what he described as pink thyroid juice.
This, in some ways, was a revolution. It meant that there was a cheap, effective way of treating these conditions of myxedema and what resulted from cretinism. And it was cheap because he obtained these thyroid glands from the abattoir.
The most famous patient, we only know her as Mrs. S, was 46 when Murray started treating her, and she had obvious myxedema with a swollen face and pale skin. And Murray started giving her injections of sheep's thyroid juice twice a week. And within 3 months, there was a miraculous improvement in her appearance. Her skin was less pale, and she'd actually improved her energy, such that Murray wrote in his notes that she could do the housework much more easily. Poor thing. Mrs. S lived to the ripe old age of 74, which was a pretty good innings in 1890.
Thyroid hormones, in contrast to testosterone, last several days in the blood, which is why these injections worked. And this made them the first successful treatment in our story. But really, Horsley and Murray had no idea what hormones were. Though successful, they were only observing the effects of glands with no understanding how they worked. To get us closer to this, it would take the invention of a truly ingenious device, one which was actually able to show a hormone at work.
You could be forgiven for thinking that this was a Swiss masterpiece watch from the turn of the century. In fact, it's an amazing device invented by a physician from Harrogate called George Oliver. What this machine is called is an arteriometer, and it's a beautiful piece. And what you do is you simply put it on the wrist where the artery is, and you can measure the diameter of the artery on a gauge.
Oliver was looking to cure low blood pressure using extracts from the adrenal glands, the glands that sit at the top of our kidneys. He had injected it into rabbits, all of whom had died as a result, but he was keen to test his extract on humans.
And some people say he even used these on his son.
Fortunately, his son survived and gave Oliver the results he needed.
What he showed was that the effect of adrenal gland extracts, as measured on his arteriometer, caused a narrowing of the arteries and a resultant significant increase in the blood pressure.
What we now know is that Oliver was measuring the effect of adrenaline. This chemical is released by a gland that sits on top of the kidneys. It produces a signal to get the heart beating faster and the blood flowing more quickly. Being able to measure the effects of adrenaline was an amazing breakthrough. But the mechanism by which it and other hormones worked was still a mystery. It would be solved just a few years later. But at a terrible price. Sadly, the crucial research to get us there would come out of one of the most scandalous practices in the history of medicine.
This is the oldest operating theatre in England. And in places like this across Europe, women were undergoing oophorectomy. That's the removal of both ovaries for such conditions as hysteria, anorexia, anxiety, and even nymphomania.
And they thought that the ovaries were a source of all sorts of mental disabilities, physical disabilities, and all sorts of things. So they simply took out the ovaries of women.
And the reason they did this was because of a huge misconception, all to do with the nervous system.
The general view was that the nervous system governed all parts of the body, including the brain. The glands were part of this system, and the ovaries in particular were the nerve centers governing each and every woman. Amazingly, it's estimated that 150,000 women across Europe had this operation to try and cure them of their womanly ailments. But far from this, they developed fresh complications.
And of course, if you take out the ovaries of women, it causes early menopausal symptoms. So, in fact, women were back to square one on it.
Doctors wanted to know why oophorectomies were causing this problem. While trying to find a solution, one man conducted experiments that would turn accepted science on its head. Joseph Halban undid the idea that glands communicated through nerves, and in doing so, he finally gave us the first clear picture of how the hormone system works.
What Halban did was he took out the ovaries and the bits of uterus and a little bit of the womb, and he transplanted these under the skin of young guinea pigs. And what he showed is that the ovaries and the uterus and the womb showed changes that you would expect to be in, if it was in situ in the animal from which it came from.
This proved that the ovaries worked if they were moved from their original site. More importantly, they carried on working even when there were no nerves connecting them to the rest of the body. Halban's discovery effectively put an end to oophorectomies, and it had a huge implication for the story of hormones as well.
By this means, he showed that the ovaries weren't controlling things by nerves, instead by internal secretions, chemical messengers which move around the body in the blood, affecting distant parts. These secretions, put together, made a new system, the endocrine system.
The definition of this new system was the final piece of the jigsaw for hormones. And with the turn of the 20th century, science had finally caught up with the forgotten observations Berthold had made. His work on cockerels, Horsley and Murray's experiments with thyroid glands, George Oliver's discovery of adrenaline, and now Halban. All of it came together to give us a modern understanding of a separate system of internal secretions constantly at work within our bodies. All that was now needed was to give these secretions a name. The story goes that at a university dinner in Cambridge, Ernest Starling, a leading physiologist of the day, coined the term that we've all come to use. As Starling sat talking with a colleague, they both struggled to find a name for these secretions that could pass to another part of the body and stimulate it directly. A scholar of ancient Greek just happened to pass by, and so they asked him.
Someone said, well, they ought to call it something like hormeo, which is the Greek word for I excite or stir up. And interestingly, Starling then gave a lecture at the Croonian Society and suddenly used the word hormone. No one had heard of it before, and that was it.
The name stuck, and today we've all heard of hormones, but you may not realize just how fundamental they are.
Every form of life that has more than one cell, every plant, every animal, from an earthworm to a killer whale, uses hormones.
There are more than 80 known hormones in humans alone, and they all have vastly different roles. If you're feeling stressed, that's one of the stress hormones, cortisol, at work. If you're preparing for exercise, adrenaline will kick in, that well-known fight or flight hormone. Hormones even have a hand in the bonding process. That one's oxytocin. But what are hormones? Well, there are different types, amines, peptides and steroids, and every single hormone has a different molecular structure. But what unites them is how they work. Each hormone is aimed at a particular target cell. Strange as it may be, let's imagine I'm a hormone heading for my target. Each hormone flows through the bloodstream, passing over billions of cells. But they will only have their desired effect when they reach the right one, a cell that matches their specific chemical structure.
You see, hormones only work at specific cells. Anywhere else, it's like trying to unlock a door with the wrong key.
Okay, wrong cell. Let's try that again.
At these specific target cells, the key fits perfectly, and the hormone effectively unlocks the cell to get it working.
Once the hormone acts on its target cell, it can change the way it behaves to make it perform a specific task. For example, when adrenaline reaches the heart, it makes it beat faster. Each hormone has its own unique role.
Hormones have many different actions and many different timescales of action. So adrenaline has an effect on the heart for only a few minutes, whereas estrogen secreted every day has effects which last for years.
Building up over long timescales like this, some hormones can have dramatic effects on our body, as one of my former patients can help to demonstrate. At 7'6", this is Chris Greener, one of Britain's tallest men. And here he is with our film's director, James, who's a good 5'9". Chris leads a healthy, if unusual, life.
When people say to me, oh, well, what's the problems about being tall? I said, getting clothes. I have to have everything made to measure. I've had this problem for, well, best part of 50 years. When I left primary school, I'm taller than most of the teachers. I just thought that I would stop growing, but I didn't.
Chris's condition, called acromegalic gigantism, we now know is caused by overproduction of growth hormone, which meant that he kept growing and growing and growing well into his 20s.
When I started work, I was 6'7", and when I was named tallest man, I was about 7'5". So I grew about 10 inches in 7 years. Some of those years, I was probably growing in excess of 2 inches a year.
It was by studying people like Chris that the mysterious role hormones play in growth was unraveled. The story starts in the 1780s with a man similar in stature to Chris. When Irishman Charles Byrne came to London to earn a living as a human curiosity, he quickly attracted the attention of a notorious scientist and collector called John Hunter. Going against Byrne's dying wish to be buried at sea, Hunter stole his body and displayed the skeleton in a museum. And, as unethical as this was, it did leave scientists an invaluable clue. More than a century later, in 1909, the brilliant neurosurgeon Harvey Cushing tried to explain why Byrne had grown so tall. He used the skull to suggest that the cause might lie within a tiny gland that's hidden at the base of the brain. It's called the pituitary, and it's incredibly difficult to find, as pathologist Dr. Susie Lishman explains.
This is a human brain, and you can see that it's an amazingly complex and rich network of nerves controlling all of our movement, our sensations, and our higher function. So where does the pituitary gland fit into all this? Well, it's not quite as easy to see, and the only clue we've really got is this very short stalk. This is the pituitary stalk, and this is where the pituitary gland is attached. We had to remove it when we removed the brain. Now, if we have a look at the pituitary, here it is, a tiny organ around the size of a baked bean that sits on that stalk at the base of the brain, and I think you can just see the stalk that attaches it to the brain.
Back in the 1900s, Cushing didn't really fully understand what the pituitary did, but he was convinced it was important because of where it was.
And if we look in the base of the skull, we can see where the pituitary nestles in this area called the pituitary fossa. So it's very carefully protected by a ring of bone to make sure that it doesn't get damaged.
The protective bone layer convinced Cushing of the pituitary's importance, and that here lay the explanation for Charles Burns' unusual height.
And that's what was so interesting when Harvey Cushing examined the skull of Charles Byrne. Instead of having this small bean-sized area, there was a much, much bigger hole, and that's because the bone had been eroded, and Cushing deduced that that was because he'd had a pituitary adenoma or tumour that had grown, forcing the bone away.
Cushing deduced, correctly as it turns out, that Burns' height was due to this tumour on the pituitary, causing it to overproduce a hormone that tells our bodies to grow. A similar tumour had caused Chris Greener's height. As with the Irish giant, the tumour caused the pituitary to carry on pumping excessive quantities of growth hormone long past his teenage years.
They put it on the machine, pressed the button, and the needle went ding off the end, and they reckon I had over 200 growth hormones per unit of blood, when the average is about 15, plus or minus a couple.
Charles Byrne died at the age of 22, with his tumour still untreated. But in Chris's case, we were able to destroy his tumour with radiotherapy, and he stopped growing. And he's still going strong at the age of 70. Conditions like Chris's are fascinating. Though incredibly rare, they serve to emphasise just how important hormones are. And, as we shall see, the next breakthrough in our understanding of hormones quite literally transformed the lives of millions.
This is a vial of human insulin. It's a hormone, probably the best-known hormone of them all. Without it, you develop diabetes. And although that's treatable now, before the discovery of insulin, diabetes was a death sentence.
For children who don't make the hormone insulin, sugar that would otherwise be absorbed as energy passed straight through their body into their urine. This is why the disease is called diabetes. The most common form, diabetes mellitus, literally means a sweet fountain because the urine of a sufferer tastes sweet. Without the ability to store this vital energy, the child slowly wasted away to nothing and never survived beyond their teens. It was incredibly difficult to find a cure to diabetes, even though there was evidence that one organ in particular, the pancreas, might be at the root of it.
In the late 19th century, a couple of German physiologists and clinicians removed the pancreas from dogs and showed that they got diabetes. Now, this led the way to identifying the pancreas as the source of raising blood sugar levels, i.e. becoming diabetic.
This is a pig's pancreas, and it's about the same size and shape as a human pancreas, which is located in the upper part of the tummy at the back. And it's an amazing organ because it has two main functions. One is to produce digestive juices which enter the stomach through the pancreatic duct there, and the other is to produce insulin, which controls sugar levels.
This presented a problem for anybody who wanted to use the pancreas as a potential cure for diabetes.
But the trouble with the pancreas is that actually most of the pancreas is made up of cells that secrete digestive enzymes. So if you'd have just mashed up the pancreas, there would have been virtually no insulin in it. All it would have been, in fact, digestive juices.
So who was the genius to crack this problem and earn what was the first Nobel Prize in endocrinology? Frederick Banting was in fact the unlikeliest of medical pioneers. He certainly didn't hit on his revolutionary cure for diabetes while working in a well-funded lab. Rather, he was a failing GP in Ontario in Canada.
He was heavily in debt and would subsidize his income by giving lectures to medical students. And yet, he was responsible for one of the most sensational and dramatic discoveries in the whole of endocrinology.
During his research for one of these lectures, he just happened to come across an article in the little-known publication Surgery, Gynecology and Obstetrics. This referred to the possibility of stopping the digestive function of the pancreas, effectively killing off the enzymes and just leaving the hormone-producing cells to do their work.
He spent the day slogging over his notes, thinking how the body controls sugar and, in particular, how the pancreas deals with it.
He went to bed with these thoughts still running through his mind and woke quite suddenly with a surprising revelation.
And this was Frederick Banting's eureka moment. And these are the words of a note he wrote in the middle of the night. He said diabetes, spelt wrong. He was an appalling speller, apparently, but it was the middle of the night. Ligate the pancreatic ducts of dogs. Keep dogs alive till the atheni degenerate, leaving the islets. Try to isolate the internal secretion of these to relieve glycosuria. You need to be a doctor to understand that, but these were the first steps in the cure to diabetes.
He suddenly thought, if I tie off the duct that produces all these digestive enzymes from the pancreas, perhaps they might degenerate, and I could therefore isolate the few cells or islets that produce insulin and thereby produce an insulin supplement.
What Banting did was to operate on dogs and surgically tie off the pancreatic duct there. He kept them alive for 6 weeks, and at the end of that time, the digestive enzyme cells had died, and he was essentially left with a pancreas that was just producing insulin.
Amazingly, when trialled on animals, extract from this dog pancreas proved Banting's theory was right. And by January 1922, he was ready to see whether the same extract would work on humans.
Leonard Thompson had been a diabetic from a very early age, and in 1921, when he was 14, he was admitted to Toronto General Hospital, days away from death. He looked so thin, some people thought he was a famine victim. He was pale, his hair was falling out, and he smelt of acetone, characteristic of diabetes. And it was at that stage that he and his father agreed to have Banting's new experimental treatment containing insulin of what was described as thick, brown muck.
After a little refinement, this so-called muck, still made from dog's pancreas, gave Thompson a whole new lease of life.
And here's a picture of Leonard Thompson after he started treatment with insulin, and he should have been dead, but happily he was the first patient to be successfully treated, and it's wonderful because I've never seen a picture of Leonard Thompson before.
Now produced synthetically, insulin has gone on to save the lives of millions. By any measure, a complete medical triumph. In the 1920s, however, it opened the floodgates to a new wave of hormone research, with others hoping to find more miracle cures. Sadly, as we've seen before, this quest can have very unwelcome consequences.
After this great success, we go from the sublime to the core blimey, because endocrine science, for a bit, went seriously off track.
The days of Brown-Séquard may have been long behind us, but the hope for a secret to eternal youth remained. And with the miraculous survival of Leonard Thompson and other diabetics like him, the idea grew that if replacing missing hormones could cure the sick, surely increasing normal levels could enhance the healthy. Cue one of the most bizarre fads in medical history.
All across Europe and indeed the world, men began to subject themselves to an operation which was extremely perverse. What they wanted to do was to recapture their youth. This is the Prater in Vienna, the oldest amusement park in the world. Surprisingly, in the early 20th century, it was the site of a laboratory which carried out quite remarkable experiments.
The Biological Research Institute on the grounds of this park also went by the nickname of the Vivarium. And it was here that physiologist Eugene Steinac developed a procedure which he claimed could reverse the aging process.
This lab was particularly interested in changing the body's natural processes.
Steinac proposed a very similar technique to the one Banting had used to obtain insulin in the pancreas, tying off the duct from a gland to isolate one particular hormone within. This time, however, he wanted to isolate the male hormone testosterone, and for that, he had a very different organ in mind.
Steinac's procedure was to tie off the tube carrying the sperm, in modern parlance a vasectomy. What he thought would happen was that this would create more room for the hormone-producing cells in the testis, and this would give his patients more vigor.
Hard as it is to believe, the Steinac was a sensation, with people flocking to have it done on themselves, including some rather high-profile patients. Among them was the famous poet William Butler Yeats.
At 69, Yeats was in poor health and really quite depressed, and he had writer's block. But after the procedure, he noticed a huge increase in his creative powers, as well as his sexual desire. Interestingly, some people think Yeats wrote his best poetry after the procedure.
A young man in the dark am I, but a wild old man in the light. Then said she to that wild old man, his stout stick under his hand, love to give or to withhold is not at my command.
And it wasn't just his poetry. A few months after the Steinac, Yeats took up with an actress who at 27 was 42 years younger than him.
Had Steinac stumbled on the secret of eternal youth?
Well, of course he hadn't. And just as with Brown-Séquard, there was no way to reproduce the results he'd claimed.
We now know that there's no scientific rationale, and that it was another scientific blind alley.
Endocrinology had come a long way by the time we reached Steinac. But his procedure failed because his understanding of how hormones work was far too simplistic.
Steinac thought that the more testosterone there was circulating around the body, the more invigorated you became. But the problem was, it wasn't that simple.
First, Steinac was wrong to think that tying off the sperm ducts caused an increase in the male sex hormone testosterone. But more crucially, even if he could have raised its levels, he completely misjudged what would happen.
There's only one part of the endocrine system he hadn't understood, and that's the most important part of all.
Steinac had no idea how hormones are regulated. But the publicity around his claims spurred on a huge amount of research, and out of this came an explanation of where he'd gone wrong. And more than this, it gave a new understanding of a key role of a tiny gland we've met before, the pituitary. As well as producing growth hormone, the pituitary has the crucial job of ensuring that the levels of many hormones never get too high or too low. And that's why Steinac's technique couldn't possibly have worked. Even if you overload the endocrine system with testosterone, normally the pituitary will step in to bring the levels back down again to normal. In many ways, the pituitary works just like a household thermostat. It can sense if hormone levels have gone wrong and send messages to some of the major glands, getting them to produce more or less hormone as needed. The discovery of this aspect of the pituitary was a real milestone in my field. Even when I was a medical student in the 60s, this tiny gland was still considered the linchpin to hormone regulation. But what I love about this story is that it never stands still. And even in the last few years, research has uncovered an entirely new system of regulation which has led us to broaden our views. In fact, this system is challenging our perceptions of not only how we control hormones, but indeed how hormones control us. Professor Sadaf Farooqi has been working at the cutting edge of hormone research for more than a decade. She and her team have been studying the role of hormones in obesity. And in this condition, hormones work in a much more surprising way than we ever imagined.
So the first real breakthrough emerged with the discovery of a completely new hormone called leptin, which was first found in mice which were severely obese. And this really paved the way for finding out an entirely new system for how weight is regulated. And this system depends upon the hormone leptin, which is actually made by our fat.
It was a discovery that was entirely unprecedented. A hormone produced not by a gland, but by cells which no one thought had any part in the endocrine system.
And this is not something we had realized before. We didn't know that fat could make hormones. We knew that fat is there to store extra calories. But this was a really important discovery because we learned that fat could make a hormone that circulated in the bloodstream and acted in the brain to control our weight.
Incredibly, with this hormone, our fat cells themselves can control how much we eat by setting up their own feedback loop with the brain. It works like this. Leptin is constantly being produced by our fat cells, and the more fat stores we have in general, the more leptin flows in the blood. This essentially tells our brain that we've eaten enough and we lose our appetite. But where Sadaf's work comes in is when this system doesn't work properly, and for some reason the fat cells don't make leptin. Sadaf is still working to understand all the reasons behind how this can happen. But by figuring out one cause in particular, she has already made a fantastic discovery. Remarkably, a patient's inability to produce leptin can, in some cases, come down to their genes.
A key part of how we discovered the role of the hormone leptin was using genetics. And we were able to look at the DNA of patients and find that they had a mutation or a gene defect that was disrupting the hormone leptin. And this was the cause of their weight problem.
In the rare case that someone has this faulty gene, they will be unable to control their appetite, and so will eat more than their body needs. And this will inevitably mean that they become obese.
Up until that time, most people thought that actually your tendency to gain weight was purely down to self-control. It was purely down to the food you eat and the exercise you do, and there wasn't really any biology involved. Actually, what we showed through the discovery of leptin and its lack in patients is that, in fact, genes can play an important role in controlling our weight, and they do so by affecting our appetite. And leptin is a key regulator of appetite.
It's an incredible discovery that hormones are a key factor in our ability to maintain a healthy weight. And the fact that even a person's appetite can be marshaled by a hormone has given people new hope in the battle against obesity.
That really meant that we could find treatments for those patients, and we were able to give them leptin back, and we did that by giving them injections which they take twice a day. And thankfully, it's worked incredibly well. And now they live entirely normal lives, they are a normal weight, and many of the other health problems that they suffered with have been corrected.
With the simple introduction of leptin, Sadaf has been able to effectively cure obesity in those patients who would otherwise have no control over their weight. It's a striking example of the power of hormones, and alongside other recent breakthroughs, it suggests that we are on the verge of discovering a whole range of new hormones with potentially breathtaking capabilities.
Well, it's fascinating, really, because we've come from understanding what the classical endocrine glands were, i.e. from Brown-Séquard and everyone mashing up a few glands, to realising that actually most of our body now produces hormones. And I think in the future, the discovery of new hormones is going to be absolutely vast.
Work like Sadaf's forces us to reassess whether what we do is down to free will or simply our hormones. And it's a heady thought to think that one day we might harness the power of these chemicals to control almost every aspect of our biology. But there are lessons to be learnt from the history of hormones. Stories like oophorectomies and the search for eternal youth remind us that a little bit of knowledge is a decidedly dangerous thing. Even now, we mustn't assume that we have all the answers. As soon as we think we understand hormones completely, a new discovery will come along and prove just how little we know.
It's extraordinary that the study of hormones is only just over 100 years old. There have been some amazing discoveries, and yet it's a science that is in its infancy. And for me, the ongoing fascination is that it's going to be many years before hormones reveal all their secrets.